I would like to talk also a little bit about the dwarfs, but I will not talk about numerical simulations. We heard enough about that, and I think it's all great work, but of course you always need to test your simulations with observations. So I would like to tell you something which I saw at the beginning of this year, and I was really puzzled about that, and I started thinking about this. I don't really have a very good answer to this observation, and we might have seen it, but I give you an idea that we had, and of course now come the numerical simulations to see whether this idea makes sense or not. So this is about a work that has been done by Ibata et al. They published it in Nature, and they were looking at the dwarf galaxies of the Andromeda galaxy. They had 27 dwarfs. Of course, there are more, but they wanted to get precise distances for the dwarfs, so they focused on those that are easily seen, which are in the outer parts of this galaxy. So they got homogeneous distances, and by that also a three-dimensional position in the sky of these dwarf galaxies. And in addition, they got radial velocities of the dwarfs. And when they looked at this data, they found something which is really very exciting. So here you see these 27 dwarf galaxies. This is the Andromeda galaxy M31, and there are two smaller galaxies, the small galaxies which you all know, M32 and NGC 205 in the inner parts. Now you first recognize that the dwarfs are all in the outer part, so that's roughly 100 kiloparsecs from the galaxy, and the reason is that you have too much crowding in the inner region. Of course there are lots of other dwarfs in the inner region, but you can't really get distances very well for these objects, so that's one has to take this into account. That's not a complete sample of dwarf galaxies. But you also can see that a substantial fraction of all the dwarf galaxies in the other parts are in this kind of flattened structure. You need to think of that. You're sitting there and you look at this galaxy. This is seen from the here galactic longitude, galactic latitude, and they seem to lie in a structure in the plane that is exactly perpendicular to the Milky Way plane, and basically you see this plane edge on. Now they say there are 15 out of the 27 galaxies that are confined to a planar structure perpendicular to the Milky Way disk. It turns out these galaxies were gas deficient, so they had their blowout, they had their star formation. They had star formation obviously because otherwise you wouldn't see them. And then there are these other galaxies which are isolated, and some are more distant even, and they might have actually a little bit of gas. Now, yeah, well, no, you see this plane edge on, that's what they claim. Yeah, well, let me talk about this. Yeah, okay. That's exactly the question. You know, if all galaxies would lie in this kind of elongated structure, then you would have a clear case. So the question is, if you have 27 galaxies and you try to find some elongated structure, of course you will always find some. The question is 15 enough to make a strong case? And they discuss that, and basically what they find is they have the three-dimensional part, so also the direction towards us. They see the plane has a kind of a diameter of 400 kiloparsecs and a thickness of 12 kiloparsecs, and then they distributed 27 satellites randomly and found out how often 15 satellites would lie in such a thin plane. And they find that the probability that this is a real structure is 99.9%, that only 0.1% you would get this accidentally. Yeah. Okay. So this is. So they claim there is this kind of plane in the sky, but there's more.
I could draw a line in with 5 galaxies, 7 galaxies, from the left top to the bottom right.
Well, you can do this, but you wouldn't get 15. Yeah.
You understand?
Yeah. Well, okay. You know, there's more evidence. You know, this might not be enough. Yeah, I agree with you. But there's more evidence, and this evidence is shown here. So if you take those 15 satellites, here's M31. Here is now the Milky Way, and these are the line of sight velocity measurements. Then you see that they're actually rotating in the same direction. That means all the satellites that are below M31 with respect to us, to the south, are moving towards us, whereas all the galaxies which are above M31 are moving away from us. So they say if you add this, if you would have a random distribution of velocities, a random distribution of galaxies, 27, and then how likely is it to find this feature, then you actually find that the likelihood would be 0.002%. So this is a significance now of 99.998%. Well, don't debate with me about these observations. These are the observers. They gave us this evidence, and the question is, yeah?
The more galaxies we get, the more satellites on the right, which probability of that in any region should be 0.
Yeah.
It shouldn't happen. It's only because the directions are not showing galaxies behind.
Huh? Well, that I don't do. Well, okay, let me continue. Okay, Mark, you tell this guy over there to be silent for a moment. You're the chair, and I just simply have to do this. Okay, good. So let's continue, but it's a good discussion. I agree with you partly. I'll tell you more about this later. Actually, I get to this point at the very end. Good. So the situation seems to be the following. You have Andromeda a little bit inclined. You have this kind of plane of satellites, and the satellites orbit in this direction. Then they argue in this kind of paper that structures like that have been seen before. There's some structure, you know, a plane of satellites or that has been discussed in the Milky Way, in Centaurus A and M81. Structures like that have been found. And now the question is, suppose that this is real. How could you ever explain it? How could you form such a flattened, very elongated disk in cosmological simulations? And well, there are two possibilities which I think one can rule out. One is that actually these 15 satellites or so came in as a group. This has been suggested, for example, for the Magellanic Clouds. You know, the LMC, the SMC, they are interacting. If you would put two massive clouds into the halo of the galaxy, how likely is it that they would interact? It would be 0, so they must have come in as a group, and probably that's the reason why they are interacting. Now, it's more difficult to do this with 15 satellites, you know. How likely is it that you have a system of 15 small objects coming in together? So I think that is quite unlikely. In addition, these disk satellites have the same chemistry as the other satellites in the Andromeda galaxy, so it doesn't seem to be a separate group that fell in. And finally, it's very hard to explain, even with phase mixing, that this group came in as a compact group and then spread out over 400 kiloparsecs. That doesn't really make much sense to me. Another possibility that has been suggested is that these are tidal dwarf galaxies. So something interacted with the Andromeda galaxy. It was a disk galaxy, gas rich. It produced these tidal arms, and then in the tidal arms pop out these dwarfs. But this seems to be unlikely for several reasons. One of them is that we seem to know that the dwarfs are highly dark matter dominated, and tidal dwarfs are never dark matter dominated because they form by gaseous condensation and not by dark matter halos accreting gas. And in addition, you know, if these dwarfs would not have dark matter, they would disrupt very quickly. And we know the stellar population, these dwarfs, is very old, 5 to 9 gigayears. So that doesn't make sense too. So these two things are ruled out. So you can say, okay, well, what else can it be? The answer seems to be trivial. You just go to cosmological simulation, and it should pop out. If this is a structure that is real, and if our simulations make sense, and we have a predictive power in our numerical simulations, we should see these structures. Now, if I look at the cosmological simulation, I have a big problem. I don't get 27 dwarfs, I get thousands. It's already a problem. I can't, you know, too many. So this is, then I can choose. Yes, exactly. I can certainly make any planes I want, any structure I want. I can make one of your little dwarfs, you know, paint some dwarf there, and then I find satellites in the dwarf. So the question is, first of all, why are there only a few satellites seen? This is the old problem. And could these few satellites lie in a global structure? Could the reason or the origin of the structures explain why these satellites are being seen and why the other satellites are dark. So you need a special infold procedure, something special to happen to make satellites visible. And all the other satellites are then not visible. And so could these large structures tell us something of how stars form in these satellites and how they become visible? So that's the question. And we come up with a little paper, Tobias Gerd and me, just thinking about what could form such an extended disk-like structure by cosmic accretion. And the best choice for us is if you have cold streams. Now the cold stream scenario has been discussed by Avishai, has been pioneered by Avishai a long time. And Avishai actually told me once, which I fortunately remembered, that actually the streams tend to lie in the plane in the first place. But we assumed maybe they are not aligned in the plane. Just take a random number of streams and assume that the satellites which we see around galaxies actually came in the streams. Now if you look at the streams here, these two simulations, Mare Nostrum and Daniel's simulation with Avishai and Bono, then you basically see that indeed satellites seem to fall in towards the central galaxy along the streams. So the streams are satellite loaded, and these satellites then might form a planar structure around the central galaxy. So the question is, how likely is that? So we worked on the probability to have n of the m streams at an angle that is so small that you would form this extended disk, which has been observed. And it turns out to be very simple. If you look at this figure over here, if you have 3 streams, then as the streams all meet in the very center, 2 streams will always form a plane. Which means that 60% of all the satellites, if all the streams are equally loaded, should lie in the plane. We only need 50%, so it's trivial. You get it for free. Of course, you can say one stream is more loaded than the others. Then you got even more satellites in the plane, because you take this stream and add any other stream, and you get more than 60%. This is seen up here. So 60% is easy. You know, the likelihood to have all the satellites in the plane is only 20%. So that's, again, very unlikely. Now, if you go to 4 streams, you see that, again, 2 out of 4 will always form a plane. So 50% you get for free. 75% is with a likelihood of 60%. So it's, again, very likely. And the same is true for 5 streams, actually. Then you get 40% for free, because the 2 are always forming the plane. But also the third one being very close by gives you a 60% with a very, very high likelihood. So we say a stream environment, satellites falling in the stream can easily form a plane. 50% or so will be in the plane. The other streams might add debris, but finding 50% of a satellite in the extended structure with an angle, opening angle of only a few degrees, is trivial. So this might be evidence, if you see this kind of structures, that might be evidence for stream-fed satellite accretion. Now, of course, there are many problems. This is a very simple geometrical argument. And these problems require numerical simulations. One of them is how likely is a cold stream scenario, and how often does this phase happen, and for how long? You know, there might be phases when galaxies accrete along streams, but do they accrete all the satellites along streams or not? Did that happen to Andromeda? Andromeda is part of the local group. In such an environment, can a stream occur or not in the earlier phases? Not now, but in the phases when the galaxy is formed. Another reason, a problem is that these cold streams might wobble. They might not be linear, you know, going out to infinity and everything falls in along the same direction. They might change shape. So if you wait a little longer, then the satellites coming in later come in from a different direction than the ones that come in earlier. I don't really know. These are things that need to be worked out. And of course, as I told you, we don't get 27 satellites. We get many, many, many more. So let's say 1,000 satellites. Do they all come in a stream? This is completely unlikely, and I don't think that is seen in the numerical simulations. So we need to work out why should those satellites that come in the stream, which form such large structures, be visible. And one reason is maybe that these satellites, yes, I'm almost done anyway, that these streams are gas-rich. And the gas richness might allow the satellites to accrete gas, even if they blow the gas out. This might form a bubble around the satellite. The bubble cools and the gas falls in again because you have a higher pressure in the environment. Of course, you could turn the argument around and could say a satellite moving through a cold stream actually strips gas. Because if there's some relative motion between the stream gas and the satellite, you strip the gas. So, you know, it needs to be discussed and understood in greater details. Now, having said all that, I get to the argument which we had in the beginning. This is not all. There is some additional complexity in this kind of observation which I haven't yet mentioned, which I also don't know how it fits into the stream arguments, but it's still fascinating. So this is seen now, this is now looking at the satellite system from Andromeda itself. So we sit in the center of Andromeda, look at the sky, and then we see those satellites in this plane. And as I said, the Milky Way lies also in this plane. So if there are stream-fed satellites towards Andromeda, how likely is it that another galaxy close by is also lying in the same plane? Maybe it's a global plane, and both the Milky Way and Andromeda were in this kind of stream environment. But what is even more interesting is that if you look at most of the satellites, here's the Milky Way, as I said, they are not randomly distributed around M31. They're actually in between us and M31.